This is a standard integer factorial. To find the factorial of 5, you multiply 5 by every positive integer below it, stepping down discretely until you reach 1. But this discrete multiplication logic reaches a limit when the input isn't an integer. If we want the factorial of 1/2, standard counting methods give us no way to determine how or where to begin the multiplication. We visualize this problem by plotting integer factorials as coordinates on a Cartesian plane, creating isolated points separated by empty space. Our objective is to find a single continuous curve threading through these points, allowing us to evaluate any value along the line. This isn't just a numerical exercise. A continuous factorial lets us apply real-world continuous analysis to a rigid, discrete sequence. To find this curve without resorting to guesswork, we look to Walter Rudin's principles of mathematical analysis. Rudin emphasizes that higher mathematics requires us to build our definitions from the ground up, using axioms rather than relying on intuitive sketches. To bridge the gap between these discrete points, we have to move beyond basic algebra and utilize the mechanics of continuous accumulation, integrals. The goal is to identify a specific improper integral whose area perfectly replicates the behavior of a factorial. Defining this integral rigorously provides us with a formal definition for the gamma function. The gamma function is formally defined by this integral, which operates over a domain from 0 to infinity. The function relies on two competing forces inside the integral, a polynomial growth term and an exponential decay term. Because this is an improper integral extending to infinity, we must prove that the area under the curve is finite and doesn't simply diverge. As the variable t approaches infinity, we can graph the two components. Notice how the exponential decay curve forces the rising polynomial curve back down toward the x-axis. In calculus, exponential decay universally overpowers polynomial growth, which ensures that the area on the right side of our integral remains finite. Now we have to look at the opposite end of the integral, the lower limit as the variable approaches 0. By restricting our input to positive numbers, we prevent the function from creating an infinite singularity at 0, keeping the output stable. With these boundaries established at both 0 and infinity, we have a finite, stable function that we can now manipulate. To see if this integral truly functions as a factorial, we need to determine if it shares the same recursive relationship. We are looking for this specific relationship. Gamma of x plus 1 should equal x times gamma of x. We can derive this using integration by parts. We'll set up our substitution by assigning the polynomial piece to u and the exponential piece to dv. When we evaluate the first part of the formula across our boundaries, from 0 to infinity, the entire term vanishes. The 0 bound eliminates the start, and exponential decay eliminates the end. This leaves the second part of the integration by parts formula. Pulling out the constant x leaves an integral that perfectly matches our original definition of the gamma function. We can now replace that integral with the gamma symbol itself. This algebraic proof confirms that our continuous integral follows the exact same step-by-step logic used in discrete factorials. Now that we have the recursive rule, we need to test it against actual integers to verify that the values align. We'll start with the simplest case. Evaluating the integral for an input of 1 gives us a result of exactly 1. Now we use our recursive equation for the next integer. Gamma of 2 equals 1 times gamma of 1, so the result remains 1. Moving higher, the pattern emerges. Gamma of 4 becomes 3 times 2 times 1, which is 6. This confirms that for any positive integer n, the gamma function is equal to the factorial of n minus 1. This one integer offset is a common point of confusion, but it is necessary for the calculus to align with the discrete factorial sequence. Because this integral accurately reconstructs the discrete factorial at every integer point, we can now use it to calculate the values in between. This brings us back to the original question: what is the factorial of 1/2? Within the gamma framework, the factorial of 1/2 is equivalent to finding the value of gamma of 3/2. Let's look specifically at the base case, gamma of 1/2. To solve this integral, we use a variable substitution, setting t equal to u squared. This transformation turns our integral into the Gaussian integral, the function that describes the standard bell curve. We can solve this geometrically. If we rotate this curve around its center, we create a three-dimensional volume that can be calculated using polar coordinates. Because the solution involves circular rotation, the constant pi naturally appears in the calculation. The final result is that gamma of 1/2 is equal to the square root of pi. We can now use this to solve larger fractions. For example, gamma of 7/2 cascades down into 15/8 times the square root of pi. The appearance of pi, a geometric constant, inside a counting function like the factorial suggests a deep connection between discrete numbers and continuous geometry. By extending these operations into continuous domains, we uncover the underlying structures that link different branches of mathematics together. This transition from discrete counting to continuous analysis has significant applications in the physical world. In statistics, the gamma distribution is used to model variables that are always positive and often skewed, like the time between events. Because the gamma function is continuous, it allows statisticians to model waiting times and probabilities that aren't restricted to whole numbers. It also forms the basis of the beta function, which is another essential tool for modeling probabilities in complex systems. Beyond statistics, the gamma function is the cornerstone of fractional calculus, allowing us to define derivatives and integrals of non-integer orders. It is also indispensable in physics, appearing frequently in the wave functions of quantum mechanics. We moved from the simple factorial of 5 to an improper integral that bridges the gaps between every integer, eventually revealing a hidden relationship with the constant pi. Ultimately, the gamma function serves as a mathematical bridge, enabling us to apply the precision of continuous analysis to discrete sequences.